So we've talked about capacitors a little bit in relation to electric field, and we've used them as an example of a uniform electric field. Now we're going to continue looking at capacitors, and we're going to define something called capacitance and look specifically more at depth in parallel plate capacitors. So let's get going. So as we learned in the last video, potential differences are caused by the separation of charge. One common method of creating a charge separation then is to move charge from one initially uncharged conductor to a second initially uncharged conductor. Now, regardless of whether we move positive charges or negative charges, which are really, when we say positive charges or negative charges, we're really talking about protons and electrons. So regardless of whether we move positive or negative charges, putting them onto initially uncharged conductors results in a positive charge on the one conductor and a negative charge on the other conductor. Two conductors with equal but opposite charge form a capacitor. The two conductors that make up a capacitor are called its electrodes or plates. The two plates are separated by an insulator, what we call a dielectric. The dielectric can be almost anything that does not conduct electricity. It can be paper or plastic, rubber, wax, air, that sort of thing. So capacitors can be really small or really large. Most of them are made up from metal foils separated by a thin plastic or paper sheets, and these things are rolled up and put into little metal cans for the bigger ones, or covered with a big glob of plastic or ceramic if they're small. This picture here shows a variety of capacitors, and this one shows the parts of the capacitor. And when we talked about Leyden jars too, we said that a Leyden jar is really just a primitive form of a capacitor. So the purpose of a capacitor is to store charge. Okay. Once we get the charges to move from one plate to the other, which sets up a potential difference, the capacitor can be removed from whatever caused the charges to move, and then that separation of charge stays put on those conducting plates because those charges have nowhere else to go. So a capacitor is kind of like a battery. We'll talk more about what is happening inside a capacitor during that charging process in a bit, but for right now, let's take a look at this picture here. So this picture is showing how the electric field and the potential difference increase as the charge on each electrode increases. If we double the amount of charge on each electrode, then the work that's required to move a charge from one electrode to the other also doubles, which implies a doubling of the potential difference between the electrodes. So the charge on a capacitor is directly proportional to the potential difference between the electrodes. Now, as we'll see, this is actually the most common way that a capacitor is used. A source of potential difference, such as a battery, is connected between the electrodes, causing a charge proportional to the potential difference to be moved from one electrode to the other. We call the relationship between charge and potential difference capacitance. And we can write this relationship as a capacitance is equal to the charge divided by the potential difference across the two plates. Capacitance depends on the shape, size, and spacing of the two electrodes. A capacitor with a large capacitance holds more charge for a given potential difference than one with a small capacitance. The unit for capacitance is the farad, whose symbol is an F. The farad is named after a famous electricity physicist whose discoveries we've not yet gotten into, but don't fear, we will. His name is Michael Faraday. A farad is a coulomb per volt. The farad is a very large amount of capacitance. So when you look at a capacitor, you often don't see just farads listed. Mostly you'll see microfarads, which are 10 to the negative 6, and picofarads, which are 10 to the negative 12 farads. Okay, so there's our basic definition for capacitance. Let's take a look now at how capacitors get charged up in the first place. So to charge a capacitor, we need to move charge from one electrode to the other. The simplest way to do this is to use a source of potential difference, such as a battery, as shown in this picture here. Now, a battery works simply by using its internal chemistry to maintain a fixed potential difference between its terminals. Basically, it uses an electrolyte chemical to separate charge and maintain a potential difference. We have positive charge on one end and negative charge on another. When a conductor, such as a wire, is connected to either end of the battery, those separated charges are then given a pathway through which to travel. The charges that move are typically electrons. We call this then a circuit. When various circuit elements are placed in the path of charge movement, the energy in those charges will be converted to other forms of energy and be used to do useful things. Circuits will be the focus of Unit 5C, but for now, just know that when we attach a conductor to either end of a battery, charges can move through that conductor from one end of the battery to the other. Now, when you first put a capacitor into a circuit, the thing has no net charge. That is, the charges on the plates of the capacitor are equal. But when you put one in a circuit, the electrons flowing from the battery eventually reach one of the plates. So, if the electrons are moving from the battery to the plate, what happens to the electrons that are on the second plate when they get there? Obviously, they're going to be repelled and pushed through the conductor back toward the battery. Eventually, though, the first capacitor plate will have all the electrons that it can have. It basically kind of fills up with electrons, and the electrons on the other plate are pushed away. This results in one plate having a positive charge and the other plate having a negative charge. This flow of charge continues until the potential difference between the capacitor's electrodes is the same as the fixed potential difference of the battery. If the battery is then removed, the capacitor remains charged with a potential equal to that of the battery that charged it, because there's no conducting path for the charge of the positive electrode to move back to the negative electrode. So, a capacitor can be used to store up charge. And capacitors are used to deliver big amounts of sudden charge. They're used in flash units for cameras. A small battery puts charge into the capacitor, and then when you take a picture, all that stored charge is immediately released to a high voltage xenon bulb that makes a really bright flash of light. One of the special cases of capacitors is that we can talk about what's called a parallel plate capacitor. So let's take a look at that. So as we've seen, the parallel plate capacitor is important because it creates a uniform electric field between its flat electrodes. So a parallel plate capacitor then is a source of a uniform electric field. You'll always get a uniform electric field between the plates of a parallel plate capacitor. For our purposes here, we're going to be dealing with capacitors, parallel plate capacitors that are separated by air, not a dielectric, not a material. We'll look at those in class. The uniform electric field in a parallel plate capacitor then can be found with this equation here, where Q is the charge on the plates, A is the area of the plates, and this epsilon naught is the permittivity constant of a vacuum. So this will give us the uniform electric field in a parallel plate capacitor. And we can use this to find the capacitance of a parallel plate capacitor that's separated by air. Now, in one of our previous videos, we found that the electric field strength of a parallel plate capacitor is related to the potential difference and the spacing between the plates by this equation here, where our electric field in the parallel plate capacitor is equal to the potential difference divided by the distance between the plates. So combining these two results, we get this right here, which we can easily rearrange to this wonderful thing looking here. Now remember that this Q over V, this is the definition for capacitance, so that the capacitance of a parallel plate capacitor separated by air is C equals epsilon naught A over D, where A is the plate area of one of the plates, and d is the separation between the plates. Now the value of this constant here, epsilon naught, which is the permittivity of a vacuum, is 8.85 times 10 to the negative 12 square coulombs per Newton square meter. So if you're ever bored or anything, what you could do is you could do a unit analysis of this permittivity constant and see how those units came to be. But for now, let's just take a look at what this equation tells us about capacitance in a parallel plate capacitor. What it's telling us is that capacitance is directly proportional to the area of a plate. So if the plate area increases, the capacitance increases. If the plate area decreases, the capacitance decreases. So capacitance and plate area are directly proportional. When we look at the distance between the plates, we see that the capacitance is indirectly proportional to the separation between the plates. So if we increase the distance between the plates, we decrease the capacitance. If we decrease the separation, we increase the capacitance. Now all of this makes total sense, right, if you think about the charges on the plates of the capacitor. If we increase the size of the plates, we have more charges that we can separate, right? So if we have more charges, we can increase the capacitance. Similarly, if we move the plates further apart, we decrease the force between charges as the electrons on one plate repel the electrons on the other. If that force decreases, then fewer charges leave the second plate. If there's fewer charges, there will be less capacitance. Also, make a note that the area here is the area of a single plate, not the combined area of both plates. In the next video, we're going to talk about how capacitors and energy are related. We'll see you then.